antennas, dipoles, monopoles and loops. Series on antennas and wave propagation, lecture number 2.13. Wire antennas are the oldest antennas. They are also the earliest antennas known to mankind, used by mankind for establishing wireless communications. Important wire antennas: short dipoles with uniform current distribution and half-wave dipoles with sinusoidal current distribution. Both are considered, described and discussed in earlier sessions. In the present session, the focus is on short dipoles, short monopoles with linear current distribution, quarter wave monopole with sinusoidal current distribution, and also on loop antennas, especially on small loop antennas. We try to derive field intensity given by these radiators when they are in transmitting mode. From field intensity, one can obtain directivity, radiation intensity, power density, radiation resistance, and other parameters of interest also pertaining to these antennas. Let us begin with the distribution, current distribution over straight conductor wire antennas. Here are shown 5 vertical conductor radiators. First one is a short dipole, length is very small, having uniform current distribution. It is not a practical one, but it has tremendous theoretical importance. It is already covered in an earlier session. In B is shown short dipole whose length is also small, but current distribution over it is changing in a linear manner. At the tips or ends, current is 0. It is increasing to a maximum at the middle of the conductor. In C is shown a monopole. The structure of monopole is a vertical conductor length dl by 2 located over a ground plane. Notice ground plane is part of monopole structure. Here also current is changing in a linear manner. At the end it is 0, at one end it is 0, at the other end where it is usually fed, here current is maximum. In D is shown a radiator, straight conductor radiator antenna whose length is lambda by 2. Hence it is called half wave dipole. One can notice current distribution over this radiator is varying in a sinusoidal manner. At the ends it is 0, at the middle it is maximum. In E is shown a quarter wave monopole because its length is lambda by 4. It is over a ground plane. Current can be observed varying in a sinusoidal fashion. Out of these 5 wire radiators, A and D are already covered in earlier sessions. In the present session, we cover B, short dipole with linear current distribution or triangular current distribution. C, monopole with linear current distribution. E, quarter wave monopole with sinusoidal current distribution. And then we take up loop antennas too. Before going further, one point requires to be mentioned here, which we are going to use in the coming parts of this session. That point is, when it comes to A or B or D, structures shown in A, B and D, radiation is in all directions. Whereas in case of structures shown in C and E, monopoles, radiation exists only in upper hemispherical part. There exists no radiation in the lower hemispherical region. No radiation below the ground plane. Radiation exists only above the ground plane. A few points regarding dimensions. Short dipole is a short dipole only when its height or length is less than or equal to lambda by 10. Short monopole is a short monopole only when its length is less than or equal to lambda by 20. Half-wave dipole is a half-wave dipole only when its length is lambda by 2. Quarter-wave monopole is a quarter-wave monopole only when length is lambda by 4. So length of conductor is less than or equal to lambda by 10, it is a short dipole. If it is less than or equal to lambda by 20 and standing over ground plane, then only it is short monopole. A wire conductor is half-wave dipole only when its length is lambda by 2. A wire conductor is quarter-wave monopole only when it is standing upwards over a ground plane having a length of lambda by 4. Of course, short dipole with UCD, uniform current distribution. It carries uniform current, same current all along its length. Short dipole with linear current distribution. It carries current that varies linear fashion along its length. Short monopole also carries current that varies in a linear manner. Half-wave dipole carries current that varies in sinusoidal manner. Quarter-wave monopole too have same current distribution, that is sinusoidal. Now we enter into the actual analysis part of dipoles and monopoles. First, we consider short dipole with uniform current distribution. Here it is being mentioned because we are going to use the field intensity given by this radiator as a reference. Radiation field intensity from this dipole is 60 pi im h sin theta by r lambda. It has already been derived in an earlier session. This expression we are going to use in finding field intensities due to dipoles and monopoles with linear current distribution. Below to it is shown in a short dipole with linear current distribution. For this, we want radiation field intensity. When it is working as a transmitting antenna, what is the radiation field intensity given by it? This is what we want. For that, one simple method, simple technique is estimating the linearly varying current over the conductor with a uniform current distribution like this. The current over the dipole, it is 0 at the ends, maximum Im in the middle. This current is equivalent, linearly varying current is equivalent to a uniform current whose magnitude is Im by 2. Here Im is maximum value. In the equivalent, the magnitude of uniform current is Im by 2, or amplitude of uniform current distribution is Im by 2. These two are equivalent. Therefore, radiation field intensity given by the actual short dipole with linear current distribution becomes equal to field intensity given by the equivalent radiator whose length is dl, same as the original radiator, but current distribution is uniform with amplitude equal to Im by 2, and field intensity given by the radiator carrying uniform current distribution is E theta is equal to 60 pi Im h sin theta by r lambda. This expression we have already obtained. We use this expression to write down the field intensity in the present case. In the present case, notice current is Im by 2, amplitude is Im by 2. Therefore, we have to use Im by 2 in place of Im. It results in E theta equal to 30 pi Im dl sin theta by r lambda. Dl is length of the dipole. Here h length of the dipole is indicated by h, but in the given situation it is mentioned as dl. Therefore we have to use dl in place of h. So short dipole with linear current distribution gives a radiation field intensity that is given by 30 pi im dl sin theta by r lambda. We consider another structure, that is short monopole with linear current distribution. It is shown here. Ground plane is there, vertical monopole is there over it, and current is varying, increasing in a linear manner from top to bottom. Using image theory principles, one can replace the ground plane with the mirror image of the short monopole. When this replacement has been done, we get a structure that is shown in B. Structures in A and B are equivalent. It means both give same radiation, with one difference, of course. Structure in B, as it is, it gives radiation in all directions, whereas the structure in A gives radiation only into upper hemispherical region. Hence here the point is B is equivalent to A only for finding radiation field intensity in the upper hemispherical region. This is not equivalent to A when it comes to radiation in the lower hemispherical region. Anyway, we know well that in the lower hemispherical region, radiation is nil. We want radiation only above ground plane. To find that, we can use structure B. But structure B is equivalent to a linear dipole with uniform current distribution having an amplitude of Im by 2. If this is Im, maximum value is Im by 2 is the amplitude of the current, uniform current distribution over the dipole. For it, field intensity is given by this formula, which we have already determined. While moving further, this is the expression for field above ground plane here. Below it is 0, we know, because it is ground plane. Now we move to another structure, quarter wave monopole. In A is shown a vertical conductor, length is lambda by 4. It is over a ground plane. Using image theory principles, ground plane can be replaced by a conductor of same length but with image currents, mirror currents. When replacement has been done, a structure like shown in B results. This structure can be easily identified as a half-wave dipole because the total length of the dipole is lambda by 2. These two are equivalent. A and B are equivalent, of course, with one difference. B gives radiation in all directions, whereas A gives radiation only into space that is above ground plane. Below ground plane, field is 0, no radiation, therefore field is 0. So the equivalence between A and B, it is valid, it is acceptable only when we want field intensity above ground plane, somewhere here. When we use B to calculate field intensity above ground plane. In fact, that is what which we require. Below ground plane, we know field intensity is 0 because there is no radiation. Now we know half-wave dipole gives a field intensity. We have already analyzed half-wave dipole in an earlier session. It gives a field intensity equal to 60 Im by r cos pi by 2 cos theta by sin theta. So quarter wave monopole gives field intensity same as field intensity given by half wave dipole above the ground plane, and below the ground plane its field intensity is 0. This is the conclusion. Before going further, one or two points, important points regarding these expressions. E theta, the radiation field may be having several components, but only one component, electric field component, contributes to power flow. That component is theta component. That's why theta component has been considered here. Im is maximum value of the current. Theta is polar angle. So these expressions are in spherical coordinate system. Lambda is wavelength. R is radial distance of a field point. In all these cases, the radiator is assumed to be placed along z-axis over the origin of a spherical coordinate system. Now, after obtaining radiation field intensity, we try to estimate certain performance indicators of dipoles and monopoles. Here we consider dipoles as well as monopoles. We have two monopoles. One is a short monopole, another is quarter wave monopole. Whatever we are going to discuss here, they apply to monopoles too. Now, radiation intensity. From field intensity, radiation intensity can be obtained. S equal to E square by 2 eta. S is power density. U is radiation intensity. E is available. Substitution of the expression for E gives us S. Power density. Power crossing unit cross-sectional area. Eta is intrinsic impedance 120 pi. Power density. Power density multiplied by R square. R is a radial vector, gives us radiation intensity. If we want radiation intensity for a short dipole, we have to use its expression for field intensity in the relation for S. If we want radiation intensity for a monopole, we have to use its field intensity expression in the relation for S here and proceed further to get radiation intensity. So this is general line of computation to have radiation intensity applicable for the three types of conductor antennas we are considering here. Radiation resistance. Once radiation density S is available, radiation resistance can be obtained by first calculating total radiated power. Total radiated power, it is obtained by integrating S, radiation density or power density, over a spherical surface. The process is this. We consider the radiator lying over the origin. We consider an imaginary spherical surface with the radius, let us say R. We know the expression for E and S. So S is available at a point over this spherical surface. S stands for power crossing the surface per unit area. If I want the total power crossing this spherical surface, then I have to integrate the S over the entire area. Integration over the total spherical surface. It gives power crossing the spherical surface, but power crossing the spherical surface is power radiated by the antenna. This is the way total power radiated is computed. S dot dA over closed spherical surface. This can be equated to I square RMS R radiation resistance multiplied by square of RMS current. Now PT is available, I is available, so radiation resistance can be computed within no time for any radiator we are considering in the present session. While going further, one point requires to be mentioned. In case of dipoles, integration has to be performed over the entire spherical surface. So the limits on theta requires to be 0 to pi. In case of monopoles, however, as they radiate only in the upper hemispherical region, we have to perform integration only over the upper hemispherical surface. Limits of theta, naturally they become 0 to theta is 0 to pi by 2. This aspect has to be kept in mind while computing radiation resistance. Now directivity. From radiation intensity, total radiated power, directivity can be obtained. Directivity is 4 pi U max by Pt. This is one important parameter, directivity. U is available, U max just by mere observation, one can find U max. Pt is available, ratio multiplied by 4 pi gives directivity. In dB, it can be obtained by applying 10 log over D. Dipole and monopole, 2 monopole. As already mentioned, the discussion here applies to monopoles to beam area. From intensity, beam area can be obtained. Omega A is beam area. This is normalized intensity. This is differential solid angle. So differentiation, integration gives us beam area. Beam area can also be obtained from directivity. Omega A is 4 pi D. D has already been obtained. From D, omega A beam area can be found. Effective length of the dipole or monopole can also be obtained from current distribution I of Z. This is a basic definition of effective length. I of Z is available. In fact, we start the discussion, we begin the derivation by assuming certain current distribution. So I of Z is always available using that expression, current distribution expression here. Effective length can be found. Effective area. Effective area is related to directivity through this relation. AE is equal to D lambda square by 4 pi. D is already available, hence effective area can be found within no time. Now we move to another area of wire antennas, that is loop antennas. Loop antennas, they have a certain special significance. They are widely used as in direction finding. They are used in composing helical antennas. Several other applications are also there. All those things we are going to consider right now. Let us start loop antennas part. Loop antennas are simple, inexpensive, very versatile, and they take several different forms such as rectangle, square, triangle, ellipse, circle, and so on and so forth. These are widely used in HF, VHF, UHF bands. As field probes, they have applications even in microwave frequency band. So HF and above HF, it is their frequency band of operation. Loop antennas are more immune to noise, making them more attractive for an interfering and fading environment. Loops whose overall length is less than lambda by 10, they are called electrically small, and whose circumference is about one wavelength, they are considered as electrically large. So small, large. Small means less than lambda by 10. Large means about one wavelength. Electrically small antennas are small loop, circular or square in shape in general, and are equivalent to an infinite small magnetic dipole whose axis is perpendicular to the plane of loop. Here one point is small loop. Small loop. It may be circular in shape or square, it doesn't matter. It is called infinite small magnetic dipole. It is a magnetic dipole. It is somewhat similar or having a complementary relation with infinite small electric dipole. Small length electric dipole. Loop is magnetic dipole, whereas straight conductor is electric dipole when their lengths are lambda by 10. These two are highly useful, widely used in the analysis of radiation. So point is, small loop has both theoretical significance as well as practical importance. However, in case of infinite small electric dipole, it is only theoretical importance. Here is shown patterns of loops. This is for large dipole, whereas this is for small dipole. Notice in case of a small dipole, there is no radiation normal to the plane of the loop. No radiation. Entire radiation is in the plane containing the loop. In case of large loops, radiation is there normal to the plane of the loop, no radiation in the plane of the loop. Some important features pertaining to loop antennas. Maximum radiation occurs in the plane of loop with no radiation normal to the plane of the loop. They are very poor radiators because of their small radiation resistance and hence hardly used in transmission mode of communication system. Poor radiators, hence they are not used as transmitting antennas. The far field patterns of circular and square loops of same area are same when the loops are small, but different when they are large in terms of wavelength. The first 2 points pertain to small loops. Third point gives a comparison between small and large loops. First part of the third point says circular loops and square loops give same far field patterns when their areas are same, but this is not so when the loop itself is large. In general, the properties depend only on the area and shape of loops has no effect when loop is small. Ferrite loops. The radiation resistance of the loop can be increased by inserting a ferrite core that has a tendency to increase magnetic flux and hence radiation resistance becomes more without increasing the electrical dimensions of the antenna. In the second point in the slide, it has been told that they are very poor radiators. How to enhance their radiation capability? One technique that is used in practice is by inserting ferrite core into the loop. Some points regarding applications. These are used in the receiving mode only for their high signal to noise ratio in portable radios and pagers, as probes in field measurements, and as directional antennas for radio wave navigation. So their main application is as receiving antennas. If the signal to noise ratio is high, a null in the field pattern may be used to find the direction of arrival. With a low signal to noise ratio, however, maximum of the main lobe may provide a more satisfactory indication. Electrically large antennas have maximum radiation along the axis of the loop. So far, these 3 points in this slide, they pertain to small antennas. Electrically large antennas have maximum radiation along the axis of the loop. Their radiation resistance can be increased by increasing its perimeter and or number of turns. It can also be increased by inserting a ferrite core of high permeability in its perimeter. This point, last point, pertains to enhancing the radiation resistance. This point has already been covered in the previous slide, where it is said that ferrite core insertion into the loop enhances radiation resistance and radiating capability of the loop. Some more points. The most attractive polygonal loop antennas are square, rectangular, triangular, and rhombic. The triangular loop can be top or base driven. What does it mean? This is a triangular loop. It can be driven from top, means from somewhere here. It can be driven from base, means somewhere here in the middle. Polygonal loop antennas find applications in aircraft, missiles, and communication systems. Circular loops are used in the UHF range because of its higher directivity, and whereas the triangular and square loops find applications in HF and UHF bands because of the advantages in their mechanical construction. Circular loops in UHF range, triangular and square loops in HF and UHF bands. Used primarily in directional arrays such as helical antennas, Yagi-Uda arrays, etc. The theoretical analysis of polygonal antennas is very difficult and has been unsuccessful because of their complex structure. As a consequence, their applications also received much less attention. Certain data is given here regarding small loops. When loop is in horizontal plane, that is, when loop is in XY plane like this, when it is small, let us say field point is here at a distance of r. This is angle theta. Area of the loop is A. I is the current. Current is assumed to be uniform. I, value I. Now, the radiation field intensity E phi, rigorous analysis by approximating this circular loop with an square loop and estimating the field intensity due to these four sides of the square loop at P gives rise to radiation field intensity as 120 pi square I sin theta over R A by lambda square. Here A is equal to D square. H theta, which is equal to E phi by eta, it becomes equal to E phi over 120 pi. It gives pi I sin theta over R A over lambda square. Radiation resistance can be determined. It becomes equal to 31.2 into N A by lambda square whole square kilo ohms. Directivity can be found equal to 1.5. Effective length can be found equal to C, circumference. Effective area, it is D lambda square by 4 pi. D is 1.5. Therefore AE for the small loop becomes 1.5 into lambda square by 4 pi. Omega A, beam area, it can be determined from radiation intensity, the normalized radiation intensity, which can be obtained from radiation field intensity. Ultimately we get omega A as 4 pi over 1.5 steradians. Now for small dipoles, length less than, very smaller than lambda, half power beam width in vertical plane is 90 degrees. In horizontal plane, pattern is non-directional and hence the half power beam width in this plane is not relevant. A comparison is given between short dipole and small loop. It has been told earlier that short dipole, small loop, these are complementary radiators. There exists a lot of similarity between them. A comparison is given here in terms of field intensity, electric field, magnetic field, radiation resistance, directivity. Directivity is the same. Radiation resistance expressions differ. Electric field expression, magnetic field expressions are given. In case of a short dipole, electric field is in theta direction. In case of a small loop, it is in phi direction. Magnetic field is in phi direction. In case of short dipole, it is in theta direction. In case of a small loop. Here is shown, given a gist of information regarding wire antennas. Short dipole with the uniform current distribution, linear current distribution, short monopole with linear current distribution, half wave dipole, quarter wave monopole, small loop. Field intensities are given, radiation resistance expressions are given, directivity is given for all these radiators, effective length is given, effective area is also given, beam areas are also enumerated here. With this, we come to an end of this session, present session. To recap, in this session, the focus has been on mainly four types of wire radiators. Small dipole, small monopole with linear current distribution, quarter wave monopole with sinusoidal current distribution, and also on small loops. We considered their directivities, radiation resistances, effective lengths, effective apertures, beam areas, and some more important significant performance indices also. Hope this session is useful to you. We meet again in another session soon with a new topic.